So I'm just going to do a sound check, so I'm just going to press pause for a moment and take my attention away over to this side, and I'll be back with you momentarily. Thank you. Okay, so we're away. Alright, so let's keep going, and thank you for that. I just needed to do a check. And if you're on YouTube, please say hello. There's a type there, you can have a chat. For example, if I say hi, you can let me know that you're on board. So live chat's on the right hand side. Obviously we've got privacy and abide by our community guidelines, so we'll be following that as we go along. Okay, so we're having a look at our statistics lecture was not complete last week, so we're going to finish that off today. And today we're having a look at measures of central tendency. And so the measures of central tendency are where we paused last week, and so we're going to have a look at that today. Of course, one of your students has said hello, so thank you for coming in. That's great. Alright, central tendency, last time we talked about statistics, we talked about the need to understand a population. A population was all of the data elements in a data set, and that it was not possible through all the examples that we looked at to make comments about the population parameters, because the populations were unobtainable, and I used that idea of being unobtainable. David and somebody else has just joined us. If you guys can hear me well enough through YouTube, could you just give me a thumbs up or say yes, I can hear you well, please? Just a little bit of feedback would be great. I think it's okay, but that's always helpful for me. So we're going to move to measures of central tendency, and then we'll move off that a bit later on. The three common measures of central tendency are mean, and so we'll do some computation of mean. Median, which is also the middle score. Now an easy way to remember that is the median strip as in the road. The median strip is in the middle. I'm still getting used to this, but I know you love it. Middle of the road. And of course mode is the frequency, and we're going to discover all of those shortly. Okay, thank you very much for that feedback, I do appreciate it. So let's have a look now. I've got some maths to come up, so don't be alarmed. You know that I'm doing well to feed back for you the maths that's needed as we go. So let's just have a look at some mathematics as it appears. The sample mean is given with this particular example, and in this case what we want to say is that there are two versions of the mean. Why? Why are there two versions of the mean? What's going on here? Well, the first thing I want to draw your attention to is that we've got some Roman numerals. So we've got a sample, and we've got a population where we use Greek. So you'll notice that there, that represents the mean. X bar is also the mean, but which is which? We've already made the distinction last week about population and the need to take a sample, and so we've got X bar, which is the Roman numeral, for the mean of the sample. Mu, the Greek letter mu, is the mean of the population. So we're going to be switching backwards and forwards quite a bit between the two, but what you'll see is fundamentally their characteristic is the same. You add up those, each of the data sets, and divide them by the number. So there's a couple of rules about how we deal with that. So measures of central tendency with mean, and so we've got some values here that we can put together. Now, in our problem-solving paradigm as engineering people and as scientists, we like to have certainty, and I mentioned this last time we were together, and the basic idea is that certainty is something that is okay for a problem-solving paradigm where we do a calculation and we get an answer. But in statistics, we want to think about certainty. We want to use probability to help us, and we want to use certainty. So as we build up our measures of understanding about our statistics, we'll build a picture up that describes our data set. What we're not going to be able to do in statistics is nail down and hammer down a complete and absolute rock solid value. What we will be able to do is speak with some confidence about means and about the nature or characteristics of the data. Again, the use of language is important, and it'll come through all of the questions that we do, and the questions are going to be there to help you prepare for the exam. So look at these means, and let's think about the data set. So we've got a mean of 5, so there's our mean of 5, and we've got a mean of 6, and we've got 5 data points here. Now what do you notice about the data points? The data points are evenly distributed. Now we can do the computation because that was important, that was just there a moment ago. What's the next one? 3. The next one after that is 5. The next one after that is 7, and then 9. And we're dividing by the total number, so 1, 2, 3, 4, 5. There's 5 elements. So we get a mean of 5. That's this guy here. Okay? So it equals 5. And we're just noticing the way they're distributed. Every second number is included in this particular data set. Well, what about these guys over here? Of course, we can do the maths calculation again. 1 plus 3 plus 5 plus 7 plus 14 this time. And again, how many placeholders are there in the data set? 1, 2, 3, 4, 5. So we've got 5 placeholders. If we go ahead and do the sum, we'll get a total of 6. Okay? Now, I want you to think about the difference between those two. I don't know about you, but if I was thinking about a profession and I was going into the profession and they said I was comparing two professions, for example, and the two professions looked at the median wages, and one of the median wages was 500,000 and the other one was 600,000. Well, that's not in my world, but it might be in yours soon. 50,000 or 60,000. Those guys are interesting. 50,000 and 60,000. I suppose you could argue there's a big difference, but really there's not much difference. But what populates the data set that causes that number to come about? Well, the mean measure, if we take that in terms of salaries, we could say 10,000, 30,000, 50,000, 70,000, 90,000. So there's an even distribution of the pool of money that's available. So the average is 50,000. 50,000 is just a measure. This guy here, though, there's 10,000, 30,000, 50,000, 70,000, but then there's someone up here with 140,000. So the mean is nearly the same as the other one that's got an even distribution. This one has an even distribution until we get to the last data element, and then it's way out of the way. So this is a problem in statistics. What's the data look like? How do we determine what the data looks like? And can we make a decision about the population parameters based on our study of central tendencies, like mean? Not sure about that. Not sure, but let's continue on. So the median now, the median strip is in the middle of the road. Another measure of central tendency. The median is obtained by ordering the observations. And so once we order the observations, not all observations or data components will be in an ordinal list. So we might have to make an ordinal list, and I've referred to it there as an ordered list. This is talking about odds and evens. So if we've got an odd number of, then the mean will sit nicely in the middle. So in the case of X bar for the sample, it'll sit nicely in the middle. If it's even, we'll have to do a calculation. So just a little one for the middle too. And this is basically what this is saying here. But we'll have a look at an example of that. Now, why have another measure? I thought the mean was good. I thought the mean could tell us everything we needed to know about our data set. So why have we added another measure, a median? Okay. So perhaps there's some more information for us about a median. A median is a good measure of the centre if outliers exist. So here we're hovering around the centre, despite the fact that this guy here is called an outlier, and it represents a difference in the median and the mean. And so because the mean for this data set was 6, so there'll be a little bit of skewing. Now that's a hint, you might want to make a note of that. I know I just said it very quickly, but the relationship between the mean and the median introduces this idea of skewness. We'll do that a bit more a bit further on. Okay, so let's have a look at our medians, our median score. Well, our first example has only 4 placeholders in it, so it doesn't sound too bad. So we've got to put it in an ordinal list, and we'll order them in ascending, so that's short for ascending. So what's the smallest number? Takes me back to primary school, this particular activity. 12, and we did say, guys, that this was all about revision from high school, for those of you that did general or standard. For those of you that did calculus, you won't have covered this material before. So it's the introductory couple of weeks. After a couple of weeks, it'll start to ramp up in terms of difficulty. Alright, so we've got an even numberer. So we said before on the previous slide that if we have an even number, we have to address that by taking the middle 2 numbers. So we have to do a little calculation. So we've got to go back to our slide and do a middle 2 calculation. So the middle score will be these guys here, and we take the mean of those. So the median in this particular example will be equal to 10 plus 12 divided by 2, and so that's 11. So our median is 1122 divided by 2 is 11 for that particular data set. These guys here, 1, 2, 3, 4, 5, it's a bit easier to do. Again, we should put them in order. You can't just get the middle score. So we make a list and put them in an ascending order. And oh well, that's right, perhaps. I'm just noticing the discontent of my brother there. So the middle one is 12. So the median for that data set is 12. We have to go through the basics to get to our parts. So obviously I've typed that up, and so we can do the data arrangement again. So I'll leave that as an exercise for you to have a look at, and you can put that on your own. Now I'll finish those and I'll post those, so they'll be complete by the time they're posted. Alright, the next measure of central tendency that we're going to look at is the, sorry, I'll leave that for you as an exercise to do. Well, that's an explanation, typed up version. So the mode is the third measure of central tendency. The mode is the value that occurs most often, sometimes referred to as the frequency. And what we notice is that mode can exist. That is, the number 9 is occurring 3 times. That's more than any other particular data number in this set. 1 and 4 are appearing in the data set an equal number of times. And in this particular data set, they're all appearing at equal frequencies. So in that sense,
low battery, please charge.
So in that sense, Moses, you're probably right there. I might have got the labels incorrect, but that's okay. I'll fix that labelling problem. I can do that later. Just for now, run with me here because it's Thursday, and we did say we'd do the stats lecture on Thursday, but thanks for pointing that out to me. Oh, that's not even a technical issue, that's just a JSON issue. Alright, so going back to the mode, we've got extreme values. There could be several modes. It could be bimodal. The data set could be bimodal. There could be 2 elements. It could be multimodal. and so on and so forth. And they're just examples of that. So how do we take this basic idea and use some of our higher power processing to analyse measures of central tendency? What happens if we don't have just a few values? How many values are there in this set? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 6 in that one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's 13 in that one. Alright, so in that sense, 13. And what happens if we get a much bigger data set? So here's our data set, and we'd like to know some more about our data set. So we've basically got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. So there's 80 elements in the data set. So this is a bit harder for us to do by hand, which is why we use software prolifically in statistics. So using the data set means that we can use Minitab as an example, and this part of your training is that we've got to get used to using Minitab in preparation for all the assessments that you're involved in. So we'll get a short form output from Minitab which shows us the measures of central tendency for this particular data set, which is talking about strength of a new alloy. So if we go up and have a look at the representative data, it tells us a couple of issues. The mean and the median are very close in value, and so there's a low amount of skewness, and we'll have a look at skewness shortly. There's two modes, it's bimodal. So these are the types of questions that I could give you. I could give you a data set just like this one, and I could say, okay, I'm expecting you to draw out the measures of central tendency. So what are the measures of central tendency? And you would have to look them up and make a statement about them. And that's the beginning of the training that you're having in statistics. So that's something that we'll follow on. Alright, so I've missed, okay, so in that sense, that's brought us to the end of lecture 1, so we're going to go to lecture 2 and have a look at lecture 2. So we've caught up to where we were from the delays of last week, and so we've gone through that. Alright, so we're going on to describing data, and of course last week we had a look at, or we've just finished having a look at, measures of central tendency, and the measures of central tendency that were looked at were mean, median, mode. We'll revisit skewness and symmetry a few times just until we get the idea, and so we'll do that. Alright, this week we're moving on to measures of variability. So measures of variability, range, variance, standard deviations,
battery, please charge.
Quartiles and interquartile ranges. So there are two main ways of describing data numerically and graphically, and we'll consider them in turn. Okay, so the first measure of variability, so we've had measures of central tendency. Do you remember what they were? Now we've got measures of variability. These are all designed to help us describe the data set. They're all designed to help us understand what's happening with our data set, and in that regard this would help us characterize the data and help us to make decisions about the parameters within a population, and that's where we're headed eventually. So the range represents the difference of the largest and the smallest, so that's simply the range. So in this case here, the larger data point that appears in this set and the smaller one, so we have a range of 5. It doesn't really tell us about the shape, but it just tells us the spread. So it tells us the spread, and you'll notice that comment there ignores the distribution, which doesn't really tell us about the shape of the data. This one here also has 12, but it's the mode as well, because it appears mostly, and the minimum is 7. So 7 minus 12 is 5. So the range also tells us 5, but again, in the same way that mean didn't really show us that there was an outlier, we had to go to median to see that there was an outlier. There's nothing really in range that's showing us the stack or the way this data is distributed. Sorry. Get these little pause in lectures too, I know. Okay, so as we move forward, what we'll find is that we are now looking at all measures of variability. The first one we've looked at is range. Measures of variability, variance. So variance takes on an important part of what we do in statistics, and we'll be exploring variance the whole semester in one way or another. We'll learn a great deal about its characteristics and how important it is as a measure, in this case a measure of variability. So we're going to introduce a couple of concepts which may not be jumping out at you at the moment, but it'll take some time for us to get all of the maths under control when it comes to statistics. So here again we've got two versions. Why the two versions? Well, notice the alphabet. These are Roman, so that tells us the Roman version is sample. This one is Greek, and so that tells us it's about the population variance. The idea in the future is that we'll be able to draw on sample variance and then make a statement about population variance under certain circumstances. The difference between the two is the population is divided by n and the sample is divided by n minus 1. That's to do with the difference in the sampling errors that get generated as we sum them together. So there's a little revision of that in the Devore text. Now the other thing I want to point out to you is what's going on up here with this thing. What's this mean? So let's just have a think about the geometry of a couple of maths ideas. I'm just wondering if you could tell me, please, what does that mean to you? What's the geometric interpretation of that? While you're thinking about that, I might do one of these. What's that mean? Yes, thank you, Justin. You said the absolute value of x, but my question is, what does it mean geometrically? So if we draw it on a number line, and we have a 0, and we have a plus x, and a minus x, this guy tells us about the distance. The distance between 0 and x. So that's the geometric interpretation of this. What does this one tell us? Well, in this case here, if we've got a value x that's being varied by c above and c below, x minus c and x plus c, again it's telling us about the distance between the two. It's telling us about the distance. So geometrically, I'm not sure if that's been made obvious to you in the past, but geometrically it's a distance formula. So what's this one doing? This one's doing a similar kind of job, absolute value, which is the square of the positives, and Hannah's chimed in with a bit of help, thank you. And isn't that nice that people are engaging with me? You know, I love teaching at UTS, and I love that we're together again. It's unfortunate that we can't be physically together, but that's the constraint of our moment in time, and it's just nice that you're here with me. So we've got x minus c. So this also represents a distance. If we put that on, we can represent a distance. So this can be interpreted as a distance, so that makes this equation a bit easier to understand, because the variance really represents the distance between the mean and one of the data points. So if we were to plot that geometrically, we could see the distance between the data point and the mean. So this is a very important idea, and you'll notice that they're squared. Both of them are squared, so whenever you see the squared, that's variance. Now we're going to come back to variance, I said that, and spend a bit of time on variance, but obviously that's something that will happen over Sorry, I've just got a little issue here with my other thing. Sorry, that's the one I wanted. I do beg your pardon. That happens in lectures too, but shh, don't tell anybody. Oh no, the whole world is watching us. Okay, so in this case we're looking at the distance between the two, so that maths is interpreting the distance for us. So that's helpful. Okay, so what's another measure of variance? And it's closely related to variance, variability, and standard deviation. So again, we've got two versions. The Roman numeral version gives us the sample standard deviation. The Greek version gives us the population standard deviation, and in this case we're taking the square root. So we often use this because it's in the same units as the data itself, whereas the variance units are not. So this is a nice indicator of the distance of the data points in a general sense from their means, and so that helps us understand that. Now it characterises the data set, so we're going to spend a little bit of time on that. So typically we had these distributions before where they were evenly distributed, and then we had some that were not so distributed evenly, and maybe something like this. And if we drew a curve around them, it wouldn't be a curve that kind of looked like this. If we have a data set that has a distribution that's somewhat like this, then the mode is in the middle here, but we can see that there's a fair bit of symmetry about this particular shape. And so we think about the mean and the median, and we think about a data point and how far away it is from the mean and median. So we'll do some descriptive work like that as time goes on. So don't be alarmed by the equations. There's quite a few equations in our subject, but for our purpose we rely on the statistical software to help us. You can do it by hand, and in some instances that's exactly what we'll do, but we'll also need to have the computer generated skill as well. Okay, so in this particular example, n is 6, because there's 6 elements. And what are the measures of variance? Well, notice the language. Now I'm just drawing your attention to this because this is quite important. This is a population data set. It's just there in front of you as example 1, but what if this had said sample of size n? So that would mean a different thing. It would mean a different set of equations. So we have to take those kinds of things into account. So in this case we're going to be using the population equations. So my mean in this case is using the Greek letter mu. So we're going to sum them all together. We don't need to put them in a list, so we can just put them together this way. Plus 12 plus 14. And we had 6 elements, and so we've got a total of 11.17. And all we're doing here is just trying to get an understanding, not so much in a problem solving sense, which deals in kind of absolute results, but we're just trying to characterize the data. We've got measures of central tendency to help us characterize the data. We've got measures of variability to help us characterize the data. So in this case we've got variance, and because it's a population, again we stick with the Greek letters, and so we take our individual sets, and so we square them and sum them because that was the equation. And I'll do a couple, and then if it's alright with you I'll just do that and put the last one in, and we'll divide by 6. I can leave it as an exercise for you to do the whole thing, but our first 11.17, so it's 9, our data point minus the mean, and so on and so forth. And down the end here we have 14, and so we get a total 2.56. So that's our variance. That's an interesting number because it tells us about the variance from the mean. And then we get the standard deviation by taking the square root of sigma squared, which is equal to and we can approximate that, if you didn't mind, to 1.60 to 2 decimal places. So again, we're doing computations. We're not delving too deeply at this point into the reasons for doing them, but we are doing them. I do apologise, I just leant on the thing. Let's have a look at another example. What do you notice about this particular question? Look, it's part of the training, and I know I labour things, but this is important. What do you notice? Well, you notice that this example is about a sample. So we'll have to use the equations that relate to a sample. We've just got to notice the detail when we're doing statistics, because it can be a bit problematic otherwise. So we're going to use x bar, and x bar will be equal to the sum and so we'll have 11.25 for this particular set. To do our variance then, we'll use the variance, which we often just refer to as var, which is s squared. Now the equation for this was the sum and what was different about this? And minus 1. So we need to be mindful of that because we're looking at a sample. It's a sample. Very good, thank you. Alright, so we sum all those up, and again I won't do all of them. I'll do a couple, just to, obviously it's much easier if you use your statistical software. So I'm being a bit cheeky leaving so many out, but I think you're there and knowing what I'm doing. And the difference here will be, it won't be 4, it'll be 4 minus 1. Just notice that difference. So for the mean we did this, but for the variance we've put it this way, and we get 4.42. And again, the standard deviation is equal to the square root of the var, which is the square root of 4.42. And so we get to 0.101586. Time flies when you're having fun, and 2.10. Okay, so we're able to add some weight to the nature of our data, and so these little measures, they're all helping us characterise the data. We haven't put them together in a cohering puzzle solving problem. We're not going to do that initially for the first couple of weeks. We just need to get the hang of feeling what our data sets look like through the lens of measures of variability, measures of central tendency. What do our data look like through those lenses? That's all part of our statistical intelligence. Alright, the next measure we've got to help us is quartiles, and students often get a little bit puzzled by quartiles and how that all gets put together. However, it's not really a big deal. So the third measure of variation is called the interquartile range, and to calculate this we look at quartiles. So it's fairly straightforward, and what we notice is that we've got a data distribution and we've divided it into quarters, and hence the name quarts. So we've got the first 25% of data sitting in quartile 1, the 50% of data sitting in quartile 2, so that's worth writing down, and then 50% of the data is sitting between quartile 1 and quartile 3. That's worth writing down, and then the final set is 25. So we can characterise the full 50% of data by this what's called an interquartile range, which we'll get to on the next slide. To calculate the quartile point, we can take this equation and use it by hand, and we'll do that in the subsequent slide. Now the next slide's a little bit wordy, but it puts into practice this equation, and it talks about rounding. So if we're going to do the first quartile, where x is a whole number, then we put some rounding into play. We'll do some rounding. If Q3 is 5.75, then we'll round up to get the sixth observation. If it's 5.25, then we'll round down. So just make a note, please, of the rounding of the quartiles, because it does come up. If it's 0.5, then we take the mean of the first of the x plus 1 observations, and so it'll be the mean of the fifth and sixth. So there's a little bit of work there to process. Okay. So the interquartile range, as I've already said, is the difference between Q3 and Q1, and it tells us, characterises the data again. So it's just another measure of variation, and it quantifies the middle 50% of the data. The interquartile range is not as affected by outliers, so we say it's insensitive to outliers, and the median was a bit like that too, wasn't it? The median wasn't affected so much by outliers as much as the standard deviation or the range are. I mean, the range hardly tells us anything at all. So it's more sensitive to the distribution of the data than the range. So in that sense, we get a better feel for the shape of the data. When that's that word that I've used again without qualification. What's the shape of the data when we're looking at the data? How do we characterise the shape? Alright, so a little bit of hard labour now. We've got a particular variable that we want to look at. So we've got this long list. So I'm just going to go through and work on the list. If I turn my pen around, that'll be helpful. Okay, so 15 students. So we've got to put them into their order. So the smallest one I think is 2. So I'll just cross them out as I go. I know it's a hand calculation. You think, come on, Jason, you said this was hard maths. I get all that, but we've got to do this stuff first. Okay, so just bear with me while we walk our way through the little bits and pieces. So we've got a 7, I think an 8, and a 9. That was a bit cheeky of me to do that. 7, 8. You've got to be careful doing that, because you might miss something and then you wonder why the result's not quite correct. So attention to detail is important. What's the next one after 9? We've got a 10 there. Well, we've got a couple of 10s. Look, there's 3 of them in a row there, so we've got to put 10 in 3 times, and 10 in 3 times, and then what comes after that, we're just counting, so that's not too bad. Now 12's appearing twice, and so this is affecting our middle score, isn't it? That's why we're doing that. And then we've got 14, 15, and 19. Have I missed one more? 25. Very good. So going back to our equation was, tell us what the quartile is by doing I n plus 1 divided by 4. Okay, so for our first quartile, Q1, 1 times 15 plus 1, which is 16, divided by 4. So that's 4. Now what's that mean? What's that mean? It means the 4th position. So we've got to step along. 1, 2, 3, 4. So the 4th Q1 is the number 8. Okay, so we need to be careful of that. Alright. The next one is Q2. So in this case here we're looking at the 2nd quartile. We're looking at 2 by 16 this time, which is 32 divided by 4, and so we get 8. Oh, what does that mean? Well, it's the 8th position, so the second quartile falls at the 8th position, 4th, 5th, 6th, 7th, 8th. So we've got the 8th position, so that's that one. So I'll just bring that down to there. And what about quartile 3? So that'll be 12. So 8, 9, 10, 11, 12. So that's the 12th position. So when you're doing interquartile range, just be mindful, please, of all of the elements that go into making up your list. Thanks, there's many more that have joined us, so it's good to see you. It's good to be here with you. Oh, did I tell you I love UTS? I love my job. I love teaching you guys, and we will get there. There's some challenges ahead for us, but we will get there. I'll be providing a lot more opportunities for us to interact. It won't be just type away on a chat. There'll be other opportunities in the future as well. But I've pretty much got everything ironed out. So we're getting close to... you'll have a good semester and it'll be okay. Alright? The university is in a bit of a situation, but it's okay. I've been doing this for a long time, so I know what I'm doing. I'm listening to you. I'm answering your emails. You'll be fine. Okay, so let's come down here, and in this case we're going to talk about the interquartile range. Whoops. So it's got the number at the placeholder 12 minus the number at the placeholder 1, and so oops, sorry, at the placeholder 1, which was 8, and the number was 8 at placeholder 4, and so that's 6, and so we've got an IQR of 6, and what was our range? The upper number minus the smaller number, 25 minus 2, so we've got a range of 23. So if you like, we're collecting metadata about our data set. That's what statistics does. It characterises the data set, because before we make a statement to anybody that's interested in what we're doing with our data, we need to be certain about our facts, and one of the ways that we do that is that we pay attention to detail. Alright, how do we display some of this data to help us view the shape and to view some of this information graphically? Because I talked earlier about a geometrical interpretation of a simple maths idea, and that might not have been apparent to everybody. But for this point, what it means is that our geometric interpretation is quite important. So let's move on and have a look at our graphical displays. So we've got categorical displays. Now, at the university, I would say, as a proportion, it would be about 2/3 in this and about 1/3 in this. Is that too much? And the reason for that is, although I am in the science faculty, I probably should be saying the opposite, but a lot of research goes on outside of the science faculty as well, doesn't it? So that seems a bit rude to say that, and not everything's going to be numeric. So I don't know if it'd be half and half. I don't think it'd be that high. Certainly, why am I making that point about university research and the categories and whether it's numeric? Because, you know, this data goes places. Our understanding of statistics gets published. Society more broadly uses our information to advantage society. So everything that's happening in the current crisis, there's a whole range of statistics that have been published previously that help authorities plan and make decisions. It's not just somebody kind of winging it and going, yeah, I'll do that. It's much more informed than that. And I think I have told you in the past, if you were at lecture 1, that as we move up into these areas, we become more informed, and we have to be careful about what we imply from our understanding. The more you know it, the worse it is, so that's just a part of life, isn't it? So categorical data, and that can be split into nominal and ordinal, and these are the charts, the pictures that help us see those. So we need to have an understanding, increase our understanding of what they might mean. We've got discrete or counting, and continuous or measuring, so I don't know if you wrote those down, counting and measurement. We've got box plots for discrete, counting type tops, and histograms, and that might be new to you. And so histograms open the door to the next layer of knowledge and understanding with statistics. Alright, so in this case we've got an example, just a concept, the number of individuals in different groups. So this particular example is giving us a geometric interpretation of that proportion. So there's a word, proportion. Look at all the clerical staff in this particular employment category for this particular organisation or sector of the industry, the management, the sales force and the clerical staff, and it's been given here. This visual is a clear indicator of what's going on, where the weights are, where the costs are, where the output should be. Where are you going to make gains as a manager? Because you look at the data and you think, how am I going to improve what's happening in the organisation? Well, you do some data. Hey, we're doing data analysis. Who knew that some simple Year 12 graphs could lead us into data analysis? But that's what we're doing. Okay, what about the histogram? Well, histograms are not the same as bar charts. That's the first point. They're not the same thing. And they help us to see the shape of the data. Okay, so they give us an idea of the overall idea of the shape of the data. Who knew that that was a thing? Right? Who knew that it was such an important thing? The shape of the data. Okay? So they're not the same as bar graphs. The x-axis on a histogram is a continuous scale. On a bar chart is a set of categories. So we need to be careful about that distinction, please. And the widths of the columns on a continuous scale, we need to be careful how we choose those. So here we've got some information that's given to us. This is strength of material. There's our strength. We've got data points that are appearing at different frequencies. So this strength from this sample, so we're interpreting data by looking at the graphics. So this strength had that number of occurrences. This one was about 6. This strength, or the bucket of strength that are surrounding 120, had that number of occurrences. The bucket of strengths around 160, up there at 22-ish. If we go across and see, that's about 22. Okay, so it had 22 occurrences. So reading the histogram means looking at the data points and how often they occur. Okay, and that's why these things are frequencies. This is always frequency in a histogram, and so it's continuous along the bottom, as pointed out on the previous slide. So what do we say about the mean? Well, the mean's there and the standard deviation, so they help us characterize the data as well. Now, this is a comment about normal fit and normal distribution. So what we've got here is this lovely bell curve shape. This is a classic bell curve, what's called a normal distribution. So we say that this data may or may not be normally distributed. We can see that it doesn't fit that perfectly. It's looking pretty good as a model, but it doesn't fit it perfectly. Alright, so what happens with data sets? Well, sorry about that, folks. Data sets can appear, and we just saw an example of 160 being here, so it's unimodal, but these represent other data sets where the mode is the frequency. So these two values have got higher frequencies of occurrence than the ones around them. This one's got lots and lots of modes, so these guys are occurring lots and lots. Okay, so that's almost that's a multimodal one. And then we've got some skewing. So we've got a symmetric shape here. So our mean, now this is important, so I'd be taking a note of this. Our mean and our median are superimposed on one another for a symmetric. So X bar and the median score would be the same here. For the right skewing, you'll notice the tail, the direction of the tail is out to the right, and hence the right skewing. So in this case, where does the mean sit? And where does the median sit? Now I'm asking that question and I'm deliberately not answering it because I want you to do some work. I want you to think about the impact of the mean and the median. Which is which here? Okay, over here let's have a look at the mean and the median, and which is which. What's happening with the mean and the median? You can go onto Minitab and do some experimenting to get that out. I will tell you what it is next week, but for the time being I'm just going to pose a question. Alright, so we've got a histogram of repair time, lots of different examples that come up in the sections that we use. And so in this particular example, if I have a look at a normal distribution, what would my version of that be? Well, it's kind of heading off in a slightly different direction, isn't it? It's kind of going up like this and then coming down, and down it comes. And so we can see that there's a different curve there. So the tail's to the right, there it is. So we call this a right skew. So we do a right skew for that particular one. Alright, what's another visual aid that helps us apart from the histogram? We had interquartile range earlier. Perhaps we can have a look at those as well. And we do the box plot. So here's our box plot, and this gives us an indication of outliers. So there's our data. These can be vertical or horizontal. They don't have to be like this. In Minitab, we could go to the graph and generate a box plot. So that'd be 2 steps on our graph. And I'll do that in the labs. So when I do the tutorials, sorry, not the labs, but when I do the tutorials, I'll do some demonstration examples for you. And Monday morning the tutes will be published. Okay, so our interquartile range represents the middle 50% of all of these data points. Okay, so in that sense, just getting a message here I want to attend to. So in that way, we've got our middle 50% here, and we've got our Q3, our Q1, we've got some outliers. So what we're doing here is we're characterizing all of the data. We're putting it into the lens of a geometric interpretation. So the whisker finishes at the last point within 1.5 IQRs of Q3. So this is the tail here, so it's finishing within 1.5 of this one, above and below. So it fits there. Okay, so we can see that there's a symmetry, or if you like, they're analogous to one another to have shape. So left and right skewing, we need to be able to pick these up. Okay, this is a core skill that you need to be able to do here. So left and right skewing, and I've kind of given away a little bit about the mean and medians. Okay, now just in the last one, did you notice? What's the line? Oh, it's the median. Okay, so that's a clue to that little challenge I gave you before. So this line represents the median. Okay, so the median in each of them, and then I did make a comment about the average, so you can maybe answer those questions nearly already. Okay. So getting used to this, interpreting this data is where you'll get questions. Okay, you'll get questions in asking, where's the middle 50%? Is it left or right skewed? Imagine they were covered up and not there. Okay, so if we did this one, just took that out, and you were just given this. So you got sitting there by yourself, what's your data knowledge like with statistics? Okay. Left and right skew, the hint I gave you was the direction of the tail. Okay, so here's an example observation of time to failure for turbochargers. Turbochargers, what's a turbocharger? Okay, so it's used on a combustion engine, so your engineers, and the thing that I would say to you as engineers is don't exclude yourself. So I don't care if you're a civil engineer or an environmental engineer, It's not so much about the discipline, the content of your discipline, it's more about our statistical ideas. What's the statistics behind this idea turbocharges from a particular type of engine? So they force air into the cylinder and make it a bigger engine. Basically, that's what it does. So you can do some googling about that if you want to. But looking at the data set, what we can see, of course, is that there is some skewing, isn't there? So we've got some skewing, and the skewing is out to the left. So in this case, we've got some skewing out here. We get our hump there, so we've got some skewing our tail. So we could say left skewed. Okay, so interpreting the data, interpreting where all the data points are sitting in groups. So we're visualizing the data, we're getting an understanding of the characteristics, not just of central tendency, but of variance. Just plenty of examples now to go through. So again, how would we characterise the skewing? Well, they are both skewed, aren't they? This one's tremendously skewed. Okay, so that's a right tail, so it's got right skewing. Okay, so we're just learning to characterise the data, seeing what's in front of us. What about this guy? Well, I haven't drawn that very nicely there. I should have put a bit of concavity in there, but it's a bit more symmetric. So we can say that it's more symmetric. It's not completely as bad as this one, right skewed, and it's more symmetric, but it's still flawed in the sense that that's not sitting right in the middle. It's very close, but because of that, we can say that it's got symmetry. It's got a little bit of right skewing. Okay. Other types of plots that can be helpful in characterising our data, giving us a geometric interpretation of what's happening with our data sets so that we can be discerning about what they look like. So in Minitab we've got a graph time series plot, and so we can do a time series plot, and this helps us to look at a particular set of information over time. Now what is it about this particular information? I'm just going to go in like this a little bit. So if we look on the left hand side, it's divorce, and then we've got a couple of big things that have happened here. So these are the 1920s, this is last century. What happened here? What happened in this time period here? Look at this rate here. Wow. There was a big change in the divorce rate, wasn't there? A big step increase. Like that. So what happened there? What was going on there? Anybody want to offer? Period in time last century? Yeah, thank you Josh, I appreciate that. So also the divorce rates came back. Now it's an interesting social phenomenon. Statistics might help us explain why that was happening, and I don't want to spend too much time on it because I really want to finish this set this week. And so this is about the change in people, isn't it? It's about the change in people. Thank you, Justin. It's about the change in people, and so it's an interesting phenomena. I mean, spouses were coming back from a war-torn part of the world, wherever they were, much like the disruption that we've had here in Australia recently, and people were doing jobs to live, weren't they? They were having to go out and do the work that others had been doing, and they were doing it for them. And they thought, maybe I can have a different life. So maybe that was a social contributor. We can categorise that. We can sample that. We can find out what the population is and make a statement about that. So that's an important thing. The rates went down again, and then they went back up again here. So what's been going on globally? What's going on here? Wow, that's another big step change, isn't it? So what's happened here during this period? So maybe it's something to do with the way people are having disposable income. Maybe there's a change in who controlled the money. Maybe there's a change in societal ideas and standards generally. But anyway, we can draw out a lot of questions like that, but we can apply the maths and statistics to it, and that's the thing I want to emphasise for you guys, right? This is statistical science. This is an important part of what goes on in your world. Alright, so I might have to unzoom a little bit. Okay, so I'll just unzoom a little bit. Now, interesting. Time series plot, turnover in department stores. So what would it be like now? It'd be flat, wouldn't it? I think it'd be, up here somewhere, and it'd be flatlining. It'd be like, ooh, that'd be department store turnover. So turnover refers to money in and money out, and the difference between the money in and the money out is the profit. So I'm just wondering, some of you will be involved in businesses, and so you'll be able to put your business analytics in your engineering mind together with this. So what's happening here? In January, there's a few sales on, then it kind of goes, and then look what happens just before the next year's January. What's going on here? One, it's nearly twice as much business in a very short space of time. Anybody want to help me out? What's that one? So, what is that? What's happening there? Every year it happens. So there's a commercialisation of the period, isn't there? And these are Christmas sales. So there's a big spike. So you can see why retailers and business people in general love what happens at Christmas time. Okay, so it's very hard to get them to move on that because they're getting volumes of turnover. Yeah, Christmas period, they're getting volumes of turnover which are just significant. All right. So we're looking at graphs and what their useful properties are. So bivariate rates refer to looking at a relationship. So now we're starting to get beyond high school. We've left high school, so by high school, now we're starting to look at, it's a little bit in there, but it's not the way that we're going to be looking at it. So properties of single variables, and we've referred to the notion of data sets as data points or data elements, and we introduced this idea of a variable. So is there a relationship between variables? It depends a little bit on the type of data and the type of data being used. Alright, so let's have a look at an example. It's a little bit complicated, but we'll follow through with it. So we'd like to see if there's a relationship between two variables and whether or not that relationship can be explained. So Three Mile Island, for those that don't know, is a nuclear power station, or it was a nuclear power station in the US. And so there was a big accident there. So there's a movie made about it, and so there was a lot of kerfuffle. It was a big event in that particular part of the world. So a survey, so some data collecting happened, 150 households, 2 weeks after a nuclear mishap. The survey asked the respondents distant from the island whether or not they believe there should have been a full evacuation of the area. I suppose today's relevant question is, should there be a full lockdown? It's the same kind of debate. Should there have been a full evacuation? And so then the distances. So miles can be converted into kilometres. That's some countries use what's called an imperial method. As engineers, you'll have to learn to switch between the two. And so 1 to 6 miles, 7 to 12 miles, 13, and so on and so forth. So this data, this contingency table, is showing us who was evacuated, who wasn't evacuated, what their totals were. So 38 people lived in the 1 to 6, 34 and 78 13 plus. So in the total area it was 150 respondents. So there's our Minitab output. We've got a tabulated statistics, and so our tabulated statistics have all of the data that was in that contingency table. What percentage, now this is a good example because it's kind of your introduction to the problem of statistics. What is it about statistics that is so difficult? Well, it's knowing intimately what's going on with the data and understanding how to describe and explain that. It's just not straightforward. So what percentage thought that there should have been an evacuation? Well, it's multiplied by 100 over 1. So what percentage thought there should have been an evacuation? So the survey said, yes, there should have been an evacuation. 66 said there should have been an evacuation, and the total number of respondents was 150. So that's a lot of data on a contingency table, multiplied by 100 over 1, and that is equal to 44%. So 44% thought there should have been an evacuation. Now here's the language that comes up in statistics. What percentage of all respondents lived within 6 miles of 3 Mile Island? So all respondents, 6 Mile Island. 6 miles of 3 Mile Island. Okay, so what percentage of all respondents live within? So all respondents within 6 miles, there it is. So we're going to have to do that percentage. So again, it'll be 38 over 150 times 100 over 1, and so our percentage will be 25.3. Okay. What percentage of respondents who live within 6 miles of 3 Mile Island thought that there should have been an evacuation? Okay, so what percentage of, so within 6 miles, so here it is, that's the number, okay, but that's of the total within 6, so it's 18 over 38. So getting your data sets right and getting your characteristics right is not always straightforward. We need to be mindful of this, okay. 47 of those, that represented 47.37%. So nearly 50% thought that there should have been an evacuation living within the 6 miles. So the language component becomes very real here. What percentage of respondents who thought there should have been an evacuation live within 6 miles? So who said yes to an evacuation? Of all of those that said yes, what percentage of respondents who thought that there should have been an evacuation? Well, there were 66 respondents who said there should have been an evacuation, live within 6, so it's 18 of 66. So again, picking your data and making it fit is tricky, so you have to be careful with those. 27.27%. Right, so you can see that's a simple example, but it highlights for you what's going on with your language and interpretation of data. So that's what this early part is all about. Okay, so 2 categories. Who can display as a multiple bar chart? Just remembering that bar charts are not histograms, so be mindful of that. The categories across the bottom rather than variables, so we need to be mindful of that. Box plots can be used for a different type of catalyst, so we get to explore a lot of different ideas in statistics. So what's a catalyst? Before we can answer a question about comparison of catalysts, surely we should know what it is. Well, typically a catalyst speeds up a reaction, a chemical reaction. So what's an example of a catalyst? If you've been for a drive in a car, as an exhaust pipe, you would say, big deal, what about the exhaust pipe? Well, it has a catalytic converter in it. So there's emissions of nitrogen that are a bit hazardous when they're heated up to the temperatures that they get to, NOx emissions. So the nitrous oxides need to be sped up to become less harmful to the environment, and they do that with a catalyst, and that's called a catalytic converter. So you can Google that to get the details of all of that. So in this case here, we can see that there's some similarities between the catalysts. We can see that the values are slightly different. It's got a similar spread, but this one, look, what do you notice about the 2 data sets here straight off? So just training your eye to pick it up. That's the median, isn't it? That line across the box plot is the median. So that represents the median score, and it's really nearly symmetric. I mean, it really is very nearly symmetric. This one here, there's a long tail that goes off. So that one's definitely not symmetric. So just getting some observations and comparing the variability and the shape of the data. So we can do that multiple times. Cuckoo egg lengths. So we can see different types of birds in there. Look at the variety of data. We get to see how skewed they are. Look at that skewing that's going on there. That's the middle score, so there's some outliers. This one's, where's the symmetric one? That one looks like it's a very nearly normally distributed, so it's symmetric. This one here is also very symmetric, but we've got some skewing in this data set here, and so there's some skewing here in these guys. That's pretty symmetric, but it's the opposite way to these. So these are left skewed, and that's left skewed there and right skewed there. So big right skewer there as well. So just getting an eye for developing your understanding of a particular data set. What about when we get some odd shapes? Okay, box plot of bus travelling times. Make A and make B. I don't know if this is the same driver. I'd like to know, but if it was the same circumstances and the same driver, they're very different times, aren't they? There was a very narrow variance in make A, and it was much lower. The median score was much lower. Make B had a much larger time. So if you saw that and you were thinking about making a decision on buses, which one would you choose? So characterising the data, using your statistical intelligence to make that work for you. Alright, so some more on geometric interpretations. We've got scatter plots, price of a car versus age. Then obviously we start off with age at 0 and go that way. So by the time you get to a 20-year-old clunker, it's not worth much, but you can see that there's, depending on the earlier years, then the prices are still fairly stable. If you look at this range here, what's the box plot for that one look like? That'd be interesting. Permeability and strength. I wonder what that looks like to you guys. That almost looks like we could plot a line there, doesn't it? Is that something that we do in statistics? So we'll learn more about that, and I did enunciate that at some point in our first lecture. Okay, so we're getting towards the end, and I'm just going to keep to time. Measures of relative standing in percentiles. We want to measure the position of an observation within the data, okay, and then understand what the percentiles are. So again, just notice the frequency. The frequency is up here. Remember, in this type of graph, this is always the frequency of the occurring values. Lots and lots of values occurring around the mean in this data set. So we just got to get used to interpreting that correctly. Okay, percentile is an observation, and we've got percentile of an observation. So what we're doing is we're looking at the data set in terms of percentages. So at 0.65 or 65%, which is another way to express that, the 65th percentile is covering all of those in the population. Okay, so we can make comment about entrance scores or where we would place and how many students we want or how many students we might have access to. So just interpreting that data. If we split it up into a standardised form, then we've got our quartiles. So these are the quartiles that we had before. Quartile 1 and quartile 2, there's the middle 50%. That's the IQR. So we're just interpreting it in a slightly different way. Alright, so what we're going to do is quickly finish off today with a little look at measures of standing. So we've only got a couple of slides left. This is an introductory slide for next time, and we look at a Z-score. And a Z-score about a particular observation, how many standard deviations the observation is from the mean. So that's what a Z-score is. So it's a number. A number. So if we have a Z equals 2, then we say that it's 2 standard deviations away from the mean. If it's 25 standard deviations away. So we know our standard deviations represent a group a distance, if you like. So it represents how far away from the mean on a graph. So that's our simple computation for this. It's fairly straightforward. And again, look at your pronumerals to see what's happening there. Alright, so you've been very good. We'll have a look at some more interesting work next time. We've got to go through this early 2 or 3 weeks where we're looking at all of these kinds of things initially, okay, and we'll go through and do some more next time. Alright, I'm going to pause there. So I'm just going to pause on the video, and there's a couple of questions up, so I'm just going to have a look at them, and while that's sitting there, okay, so just bear with me. So outliers will present themselves in the data set. So the way that we'll measure the distance between the z-score, for example, an outlier will have a very high number. It'll be a very large number of standard deviations away from the mean. So things like outliers have ridiculous z-score type numbers or ridiculous numbers of standard deviations away from the mean. Thanks for that, Andy. That's helpful. All right. Yes, my intention, Justin, was to put the tutorials on YouTube. It'll be done slightly differently. You're privileged because you guys are here with me now. But basically what's going to happen is that I won't use the slides. I'll be referencing some paper. So I'll be doing things on paper for you because the tutorials cover both the stats and the maths. The maths lecture I do on paper. Okay, so I don't use the pen. I don't use the pen and the tablet in the way that I've done this. I mean, I've used Microsoft Edge if anybody's interested, and I've used the pointer to make that all happen, but I use paper for the maths component. So you've also got the previous lectures from, I think, spring a couple of years ago that you can check, and basically they're the same content. All right, but I'm happy that you came along. I'm happy to be here with you. And again, if you've got questions, you can email me, but I really want to praise you for turning up, and well done. Okay. What we'll do is we'll press pause there, and I will see you tomorrow at 4:30 for the mathematics component. And you're quite right, Moses, I need to rename those. But thank you very much for pointing that out to me. All right, take care everybody, and I'll see you next time. Bye for now.